Modern practice defines every mathematical object as a set of some kind, so this notion has to be examined first. A set is a collection of objects that is itself considered an entity. Its objects are called elements or members, and the membership symbol is a sort of capital epsilon. The equals sign means logical identity. Two sets are considered the same object if and only if they have exactly the same members. So set equality reduces entirely to one line. For every x, x belongs to A if and only if x belongs to B. If every element of A is an element of B, then A is a subset of B, or A is included in B. So A equals B is equivalent to A included in B together with B included in A. That is the usual way of establishing set identity. Prove both inclusions. A finite set can have its members listed inside braces. One member gives a unit set, two a pair set. Infinite sets are generally defined by statement frames. The set of all x such that P of x. The reals whose square is under 9 form the open interval -3 to 3. We need the empty set much as arithmetic needs 0. If P is never true, the set of x satisfying it is empty. The x that differ from themselves form the empty set. In passing, the authors note that the number 4 is usually defined as the set of 0, 1, 2, and 3. To avoid overworking the word set, the book also uses class, collection, family, and aggregate. Next, restricted variables. A variable is not allowed to take all objects as values. It can only take members of a certain set, called the domain of the variable. The domain is sometimes stated and more often implied. The letter n customarily means an integer. In case of doubt, we write it out. Read as for every n in the integers. Note that the membership symbol is read here as the preposition n. Such quantifiers are called restricted. Restricted variables are just abbreviations of unrestricted ones. The universal case unfolds as, for every x, if x is in a then P. The existential case unfolds as, there exists an x with x in A and P. One uses implication, the other uses, and they must not be mixed up. Then ordered pairs. A pair is again taken to be some set, but we do not care which, so long as it guarantees the crucial property. Two ordered pairs are equal exactly when their first elements agree and their second elements agree. So 1, 3 is not 3, 1. Correspondence, or relation, and its special case, mapping, are fundamental. Since the graph of a relation is a set of ordered pairs, and every object is now regarded as a set, it is efficient to take the graph to be the relation. A relation is simply a set of ordered pairs. From this, the domain is the set of all first elements, the range the set of all second elements, and the inverse reverses every pair. All pairs with first element in A and second in B form the Cartesian product. The analytic plane is the reals times the reals.